There is a planet in the night sky tonight that you can find without any instrument, if the conditions are right and you know where to look. It appears as a reddish point, steadier than the stars around it, moving slowly against the fixed background of the sky on a timescale of weeks and months. Ancient observers noticed that it wandered. They gave it names that reflected what they saw: a wandering fire, a red eye, a god of conflict. Every civilization that kept records of the sky has a name for it and a set of associations. Almost all of them built around that particular color and that particular brightness in the darkest part of the sky. Mars has been observed by human eyes for longer than writing has existed. And yet until the 19th century, no one knew that it had moons. That absence of knowledge was not a failure of attention. People had been watching Mars for thousands of years, tracking its retrograde loops, measuring its brightness at opposition, calculating its position with enough precision to navigate and to build calendars, and to make predictions that turned out to be correct. The planet was not hidden. It was among the most studied objects in the sky. What was hidden was what orbited it, and what orbited it was so small and so close to the planet and so dark that no instrument built before the 1870s could have separated their light from the glare of Mars itself. Asaph Hall was an astronomer at the United States Naval Observatory in Washington when he found them in August of 1877. He had been searching systematically, moving outward from Mars each night, looking for anything that might orbit the planet at a distance previous searches had not reached. He was close to giving up. His wife, Angeline, encouraged him to continue. On the 11th of August, he found the outer moon. 6 days later, after clouds had interrupted the search, he found the inner one. He named them Phobos and Deimos, fear and dread, the attendants of the god of war in Greek mythology. The names fit the tradition of naming Martian features after figures from classical literature. They also fit something else, something that only became clear much later. These two small worlds carry an atmosphere of unease about them that is hard to fully explain and that has not entirely gone away. Tonight's journey does not begin with drama. It begins with two dark, irregular, quietly orbiting bodies above a rust-colored planet in the cold space of the outer inner solar system, roughly 228 million kilometers from the Sun. Most people have heard of them. Very few have thought about them for more than a moment. That is where we begin. To understand what Phobos and Deimos are, it helps to first understand what they are not. They are not moons in the way that our own moon is a moon. Our moon is large enough to be spherical gravity, pulled it into a ball during its early history, when it was still molten and plastic enough for its own mass to shape it. It has a crust, a mantle, a partially molten core. It raises tides on Earth's oceans. It is massive enough that the Earth-Moon system is sometimes described as a double planet rather than a planet and its satellite. Phobos and Deimos are not like that. Phobos, the larger of the two, measures roughly 27 kilometers along its longest axis and about 18 kilometers along its shortest. It is not round, it is lumpy and elongated, a potato-shaped rock with one very large crater and a network of grooves across its surface that has puzzled researchers since the grooves were first photographed in detail. Its mass is so low that the gravitational pull at its surface is barely a fraction of 1% of Earth's. If you stood on Phobos and walked too quickly, you could achieve escape velocity. You could simply step off the surface and drift away into space. Deimos is smaller still, about 15 kilometers at its longest. It is even more irregular, and its surface appears smoother than Phobos's, covered in a layer of fine regolith that has softened the edges of older craters. It orbits farther out, moves more slowly, and is so faint that even from the surface of Mars, it would appear as little more than a bright star, not the dominant presence in the sky that our moon is in ours. Both worlds are very dark. They reflect only about 6 or 7% of the sunlight that reaches them. For comparison, fresh asphalt reflects roughly 4% of incident light, and old, weathered asphalt reflects even less. Phobos and Deimos sit in that same range objects so dark that they absorb nearly everything the sun sends toward them and give back almost nothing. Their surfaces have been exposed to space for a very long time, bombarded by cosmic rays and micrometeorites processed by what planetary scientists call space weather into a dark, neutral-colored crust that holds very few obvious clues about what lies beneath. That darkness is part of what made them so difficult to find, and it is one of the first things that made researchers wonder about their origin. The surface composition of both moons, measured from orbit by several different spacecraft, resembles in some ways the composition of a particular class of asteroid C-type asteroids, carbon-rich bodies found predominantly in the outer portion of the asteroid belt between Jupiter and Mars. C-type asteroids are dark, they are low density, they carry carbon compounds and silicates and water-bearing minerals in proportions that roughly match what spacecraft have measured at Phobos and Deimos. That resemblance is important. It is one of the central pieces of evidence in a debate that has been running since the moons were discovered, and that has still not fully resolved itself. Where did Phobos and Deimos come from? The simplest answer, and the one that seemed most natural when the compositional resemblance to C-type asteroids was first noted, is that they were captured. That Mars, in the early solar system, encountered two wandering asteroids on suitable trajectories and pulled them into orbit. The asteroid belt is close. Mars sits at its inner edge. The idea that Mars could have captured debris from that population has a certain geographic appeal. The problem is the physics. Capturing an object into a stable orbit from a hyperbolic trajectory, the kind of path an inbound asteroid would follow, requires that something slow the object down during its approach. Without that deceleration, an object passing close to Mars on an unbound orbit would simply swing around the planet and continue on its way or collide with it, but would not remain in a closed orbit. The early solar system was denser with gas and dust than it is today, and some models suggest that atmospheric drag in a thicker early Martian atmosphere could have provided the necessary deceleration, but the numbers are difficult to make work precisely, and the question of whether early Mars had an atmosphere dense enough and long-lasting enough to accomplish this capture remains open. There are other hypotheses. One proposes that the moons formed in place from a disk of material thrown into orbit around Mars by a giant impact early in the planet's history, similar to how Earth's moon is believed to have formed from the debris of a collision with a large body billions of years ago. In this picture, Phobos and Deimos would be native to the Martian system, born from Martian material, which would explain why their orbits are so regular and so nearly equatorial. Captured objects tend to arrive on orbits that are tilted and eccentric. The Martian moons orbit nearly above the equator, nearly in circles. That regularity is one of the strongest arguments against the pure capture scenario, and one of the strongest arguments in favor of some kind of in situ formation. But if the moons formed from a giant impact, the composition evidence becomes harder to explain. Martian rock does not obviously resemble C-type asteroidal material. The debate, in other words, has not ended. It has deepened. There is something calming about the idea that a question this old, about two objects this close and this small, is still genuinely open. The moons of Mars have been known since 1877. Spacecraft have flown past them and orbited them and photographed them in detail, and the most basic question about their past, where did they come from, is still answered with a careful list of possibilities, each supported by some evidence, each challenged by other evidence. The universe does not always reward proximity with clarity. These two dark, lumpy, quietly orbiting worlds have been turning above Mars for billions of years, and they have not yet told us everything about how they got there. Phobos orbits Mars faster than Mars rotates. That single fact, when you hold it for a moment, is unlike anything in our immediate experience of the solar system. Our moon moves slowly eastward across the sky over the course of a night, rising and setting once in just over 24 hours relative to a fixed point on the ground. It is slower than Earth's rotation. Most moons in the solar system are like this. They orbit their planets at distances large enough that their orbital period is longer than the planet's day. Phobos is different. It orbits Mars at a distance of only about 9,300 kilometers from the planet's center, less than 6,000 kilometers above the surface. At that altitude, the orbital mechanics require a period of only 7 hours and 39 minutes. Mars itself rotates once every 24 hours and 37 minutes. So Phobos completes more than 3 full orbits of Mars for every single Martian day. From the surface of Mars, this means Phobos rises in the west and sets in the east. It moves backward across the Martian sky, against the direction of all other rising and setting motions, because it is lapping the planet beneath it. It crosses the sky in about 4.5 hours, rising again less than 11 hours after it last set. In the course of a single Martian night, an observer on the surface could watch Phobos rise twice, move quickly across the sky in the wrong direction, and set twice, or before the sun returns. It is a small and dim object from that distance, about a third the apparent diameter of our moon as seen from Earth, depending on where on the Martian surface you stand. Not a dramatic presence, not a dominant feature of the night, but fast, noticeably, measurably fast, moving against the stars in a way that no casual observer could mistake. Deimos is different again. It orbits much farther out, at about 23,400 kilometers from the center of Mars, and its period is 30 hours and 18 minutes. That is just slightly longer than the Martian day. From the surface, Deimos rises in the east and sets in the west like the sun and the stars, but it moves so slowly across the sky that it takes about 2.5 days to complete a single transit. It hovers near one position for so long that it can be difficult to tell on short timescales that it is moving at all. An observer on Mars looking up on a clear night would see 2 objects behaving in fundamentally opposite ways, one rushing westward in the wrong direction, the other drifting eastward with a patience that borders on stillness. Both are tidally locked to Mars, the way our own moon is tidally locked to Earth. The same face of Phobos always points toward Mars. The same face of Deimos always points toward Mars. This is a natural consequence of tidal forces over long periods of time, the planet's gravity gradually slowing the rotation of a nearby body until its rotation period matches its orbital period exactly. For Phobos, given how close it orbits and how strong tidal forces are at that distance, the locking happened relatively quickly in geological terms. For Deimos, the same process unfolded more slowly. The result is that each moon has a near side and a far side, and the near side has spent its entire history facing the warmth and reflected light of Mars, while the far side has faced outward toward the cold of interplanetary space. Whether that long-term asymmetry has produced any meaningful difference in the 2 faces of each moon is something that spacecraft observations have begun to explore, though the data is still limited. There is something worth resting with in Phobos' situation in particular. It orbits so close to Mars that it sits well inside the Roche, limit the distance from a planet within which a body held together only by its own gravity would be pulled apart by tidal forces. Phobos survives this because it is not held together only by gravity. Internal strength, the cohesion of rock and dust and whatever structural properties its interior possesses, keeps it intact at a distance where pure gravitational self-binding would fail. But the tidal forces are not neutral. They are doing something to Phobos slowly, measurably, in a direction that has only one long-term outcome. They are pulling it apart. Not dramatically, not on any timescale a human could observe directly. But the grooves that cover the surface of Phobos, long, shallow troughs running in roughly parallel families across its face, are now thought by many planetary scientists to be stress fractures, signs that the tidal force Mars exerts on Phobos is straining the moon's interior, creating patterns of stress that propagate outward to the surface and leave visible traces. The grooves were first seen in detail by the Viking orbiters in the 1970s and initially attributed to ejecta from a large impact crater called Stickney, the most prominent feature on Phobos' surface, large enough, relative to the Moon, that the impact that created it must have come close to breaking Phobos apart entirely. Some of the grooves do radiate from Stickney in patterns consistent with impact ejecta, but others do not. They cross the surface in orientations and patterns that the Stickney impact cannot easily explain. The tidal fracture hypothesis has grown more compelling as models of Phobos's interior structure have been refined. The moon may not be a solid rock. Current evidence suggests it may be a rubble pile, a loosely consolidated collection of fragments held together more by cohesion and low gravity than by any rigid internal structure. If so, the response of its interior to tidal stress would be different from a monolithic body, and the surface expression of that stress might look exactly like the grooves that have been observed for 50 years. The interior of Phobos has not been directly sampled. What lies beneath the surface layer of regolith remains a matter of inference from orbital measurements, gravity field data, density estimates, shape models, spectral observations. The picture those inferences produce is consistent with a body that is not entirely solid, that has significant porosity, and that is responding to its environment in ways that will, over a span of time that dwarfs any human concern, lead somewhere specific. That somewhere is the question that the next part of this journey addresses. For now, there is just the fact of the orbit fast, low, precessing, stressed, and the strange beauty of a moon rising twice in a single night, moving backward across a red sky, its surface fracturing imperceptibly under a force it has been living with for billions of years. Phobos keeps going. The orbit keeps tightening. Every orbit of Phobos around Mars is slightly smaller than the one before it. The difference is not large. In any given year, Phobos moves inward by about 1.8 centimeters. That is a measurement precise enough to require careful spacecraft tracking to confirm, and it was confirmed first inferred from long baseline observations of the moon's position over decades, then refined by successive missions that measured the orbital parameters with increasing accuracy. 1.8 centimeters per year. On human timescales, that number is functionally invisible. No generation of observers will notice the difference. The moon's altitude above Mars will not change in any way that the naked eye, or even most instruments, could detect across a human lifetime. The change is real and measurable and continuous, but it belongs to a different timescale than the one we inhabit. Project it forward, however, and the mathematics becomes something else entirely. At the current rate of inward drift, Phobos will reach the Roche limit of Mars in approximately 30 to 50 million years. The uncertainty in that number comes from uncertainties in the internal structure of Phobos. A rubble pile responds to tidal forces differently than a solid body, and the exact rate of energy dissipation depends on properties of the moon's interior that are not yet precisely known. But the range is well constrained. Somewhere between 30 and 50 million years from now, it will arrive at the point where tidal forces overcome whatever cohesion holds it together. At that point, one of two things will happen. If the outer layers of Phobos are loose enough, if the regolith and surface material lack sufficient cohesion to resist the tidal gradient, then the moon will begin shedding material from its surface before it even reaches the formal Roche limit. Dust and small fragments will spiral outward and downward, depending on their size and their relationship to Mars's gravity, gradually populating a diffuse ring around the planet. This process would not be sudden. It would be slow, extending over millions of years, a long unwinding rather than a single catastrophic event. If the interior is more coherent than current models suggest, the body might hold together longer, penetrating deeper inside the Roche limit before the tidal stress exceeds the structural strength. In that case, the breakup would be more concentrated in time, still slow by human standards, but faster in geological terms. The fragments would spread around Mars's orbit, creating a debris ring, and over subsequent millions of years, that ring would slowly spiral inward, with larger fragments eventually impacting the Martian surface and smaller material dispersing into the planet's upper atmosphere. Either way, the end is the same, a ring for a time, then nothing or almost nothing, Mars will eventually have a ring where Phobos once orbited. That outcome, a planet gaining a ring from the tidal disruption of a moon, is not unique to Mars in the history of the solar system. Researchers believe that some of the rings around Saturn, Uranus, and Neptune may have originated from moons that were disrupted either by tidal forces or by collisions. The ring systems we observe today may be, in part, the remnants of moons that no longer exist. The rings of Saturn, which appear permanent and ancient from any human perspective, are now thought to be relatively young, perhaps a few 100 million years old, and were likely fed by the breakup of one or more icy moons earlier in the solar system's history. Phobos, then, is not following an unprecedented path. It is following a path that other moons have followed before it in other systems at other times. The ending is written into the orbital mechanics, into the tidal relationship between a small body and the planet it orbits too closely. There is something in this that does not feel like loss. Exactly if you hold it from a sufficient distance. Every grandmother who ever pointed out a planet in the night sky, every child who looked up at a bright reddish point and asked what it was. They were looking at a planet whose two small companions were, even then, moving through the slow process described here. The inward drift was happening when the first human eyes looked up and noticed the wandering red star. It was happening when Asaph Hall pointed his telescope toward it in 1877 and found the moons for the first time. It has been happening through every spacecraft encounter since, through every orbital measurement, through every model built to understand what lies beneath the grooved surface. The universe does not pause its processes while we are not paying attention. Deimos is different. It orbits far enough from Mars that tidal forces are pushing it outward rather than pulling it in. Very slowly, Deimos is moving away from Mars, the way our moon is slowly receding from Earth. In the deep future, Deimos will drift far enough out that its gravitational relationship with Mars will weaken. It may eventually escape the Martian system entirely. It may remain in a widening orbit for as long as the solar system itself remains in anything like its current configuration. Two moons, one falling inward, one drifting outward, both moving too slowly for any lifetime to register the change, both following paths laid down billions of years ago by the initial conditions of their orbits and the unvarying mathematics of tidal mechanics. The solar system does not have a preference for outcomes. It has only the equations. Those equations are patient. They have been working on Phobos since before any animal capable of noticing the night sky existed on Earth. They will continue working on it for 30 million years after any such animal is gone. 1.8 centimeters per year. The orbit keeps tightening. The ring waits in the future, patient and certain in the dark above Mars. The first spacecraft to photograph Phobos in any detail was Mariner 9, which arrived at Mars in 1971 and became the first spacecraft to orbit another planet. Mariner 9 had not been sent to study the moons. Its mission was Mars, the surface, the atmosphere, the great volcanic structures and canyon systems that radar and earlier flybys had begun to suggest were there. The moons were secondary targets, photographed when the geometry was favorable and the imaging resources could be spared. What came back was the first close look that anyone had ever gotten at either world, blurry by later standards, but clear enough to show that Phobos and Deimos were not smooth and spherical. They were irregular, cratered, dark. Stickney Crater appeared in those first images, named for Angeline Stickney Hall, the wife of the astronomer who had found the moons. It is the largest feature on Phobos, a depression about 9 kilometers across on a moon that is only about 13 kilometers in radius at its widest. The impact that produced it must have released energy close to the threshold at which Phobos would have shattered entirely. The fact that the moon survived suggests it absorbed the impact in some way that distributed the energy without causing catastrophic fragmentation, which is itself a clue about the internal structure, one that later researchers would return to when building models of a rubble pile interior. The Viking missions in the late 1970s improved on Mariner 9's images considerably. Viking 1 and Viking 2 Each carried orbiters designed to image the Martian surface in preparation for the landers, and those orbiters passed close enough to both moons to return photographs with resolution measured in tens of meters rather than kilometers. The grooves became visible in detail for the first time. The texture of the surface, the fine, dusty regolith, the subdued craters, the linear features that ran in families across Phobos's face, emerged from the data as a scientific puzzle that has not fully been resolved in the decades since. After Viking, there was a gap. The Soviet Phobos missions launched in 1988 were intended to be the most detailed study of either moon yet attempted. Two spacecraft, Phobos 1 and Phobos 2, were designed to reach Mars, enter orbit, and eventually release small landers onto the surface of Phobos itself. Contact with Phobos 1 was lost in transit due to a command error. Phobos 2 reached Mars and began returning data from orbit, including some of the first detailed thermal infrared images of the moon's surface. Then, in March of 1989, contact with Phobos 2 was lost as well, just weeks before it was scheduled to deploy its landers. The landers never touched the surface. The most detailed planned study of Phobos to that point ended before it reached its primary target. It would be more than 2 decades before another spacecraft came close. The European Mars Express mission, which entered Martian orbit in 2003, made several close flybys of Phobos over the course of its mission. In 2010, it passed, within about 67 kilometers of the moon's surface, the closest any spacecraft had come since the Soviet missions, and returned high-resolution images and gravity measurements that significantly refined the understanding of Phobos's shape, density, and internal structure. The gravity data in particular was valuable. It allowed researchers to calculate the bulk density of Phobos with better precision than before, and the results supported the idea that the moon's interior has significant porosity. Phobos is not a solid rock. There is more empty space inside it than a monolithic body would have. That result fed directly into the debates about origin and internal structure that have continued to the present day. NASA's Mars Reconnaissance Orbiter, Mars Odyssey, and the Mars Atmosphere and Volatile Evolution mission MAVEN have all contributed observations of the moons during their primary missions studying Mars. None were designed specifically for Phobos or Deimos, but orbital geometry occasionally brings them close enough to collect useful data. Pieces of the picture have accumulated from instruments that were pointed at something else, refined by measurements made when the conditions were right. The picture that has emerged from this patchwork of observations is detailed in some respects, and surprisingly incomplete in others. The surface of Phobos is well photographed from multiple angles and at multiple resolutions. The major geological features are mapped, the grooves have been catalogued, and their orientations analyzed. The large craters have been named and their depths estimated. The reflectance spectrum of the surface has been measured at multiple wavelengths, and the comparison to C-type asteroids has been refined. Though it has also become more complicated, the match is not perfect, and some researchers argue the surface spectrum has been modified by space weathering to the point that the original composition is partly obscured, but the interior of Phobos is still largely unknown. No instrument has ever directly sampled the material of either Martian moon. No seismometer has ever recorded the interior sound of Phobos responding to a meteorite impact or a tidal stress event. No drill has penetrated the surface. The best interior models are built from the outside, in from the gravity field, from the shape, from the bulk density, from the surface spectrum, and those constraints allow a range of possibilities that has not yet narrowed to a single answer. What is Phobos made of on the inside? Is it a solid body with a fractured surface, a rubble pile with significant internal voids, a body with a composition that matches its asteroid-like surface all the way through, or one where the surface has been contaminated by material from Mars over billions of years of bombardment? These are not small questions. The answer to where Phobos came from, whether it is a captured asteroid, an impact remnant, something else entirely depends in part on what its interior is made of. because different formation scenarios predict different interior compositions. The surface spectrum is not enough. What is needed is material from beneath the surface, from depths that space weathering has not reached, from layers that retain whatever original signature the body formed with. That is what the next chapter of Phobos exploration is designed to retrieve. The data accumulated across 50 years of intermittent spacecraft visits has built a foundation. It has also sharpened the list of things that the foundation does not yet support. The moons of Mars have been photographed in detail. They have been measured, modeled, analyzed, and debated, and the core questions about their origin and interior structure have remained open. Through all of it, patient in the way that physical objects are patient, not waiting for an answer, simply continuing to orbit, while the instruments and the people behind them work toward one. There is a mission currently in development that is designed to do what no previous spacecraft has done. JAXA, the Japan Aerospace Exploration Agency, has been building a spacecraft called Martian's Moons Exploration, or MMX. The mission's goal is to reach the Martian system, spend approximately 3 years studying both Phobos and Deimos from orbit, land on the surface of Phobos, collect a sample from below the uppermost surface layer, and return that sample to Earth. If it succeeds, it will be the first time that material from either Martian moon has been touched, collected, and brought back for laboratory analysis. The science behind sample return is different in kind from remote observation, not just in degree. When a spacecraft measures the reflectance spectrum of a surface from orbit, it is recording how light interacts with the outermost material that has been exposed to space for millions or billions of years, altered by cosmic rays and solar wind and micrometeorite bombardment in ways that can shift the apparent composition significantly. When a laboratory analyzes a physical sample, it can probe the material directly, measuring isotope ratios, examining mineral grain structures, identifying compounds that spectral observation cannot resolve, and comparing the result to the database of every meteorite and returned sample that has ever been studied on Earth. Isotope ratios in particular carry information that remote sensing cannot easily access. The ratio of certain isotopes, oxygen-16 to oxygen-17 to oxygen-18, for example, varies in characteristic ways between different classes of solar system material. Mars has a known oxygen isotope signature. The asteroid belt has a different one. C-type asteroids have their own characteristic ratios. If Phobos is a captured asteroid, its oxygen isotope ratio should match the asteroid belt's signature. If it formed from material thrown into orbit by a giant impact on Mars, its ratio should be closer to the Martian signature. A single measurement of the right isotope ratio in a returned Phobos sample would not resolve every question about the Moon's origin, but it would decisively shift the weight of evidence toward one hypothesis or another, in a way that 50 years of orbital observation has not been able to do. The sample is the key. It always was. The challenge was getting there, landing on a body with almost no gravity, collecting material from a surface that no one has ever touched, and bringing it back across 228 million kilometers of interplanetary space. MMX is designed to land on Phobos using a method adapted from experience with small body missions, notably JAXA's own Hayabusa 2 mission, which successfully collected samples from the asteroid Ryugu in 2019 and returned them to Earth in 2020. The lessons from Hayabusa 2 about navigating near a low-gravity, irregularly shaped body, about surface touchdown procedures in the absence of meaningful gravitational force, and about sample collection under uncertain surface conditions directly informed the design of MMX's landing system. The landing site selection for Phobos has been an area of active research and debate. The surface is not uniform. Different regions carry different histories. Areas near Stickney crater have been influenced by the impact and its aftermath, while regions on the far side of the Moon from Mars may have accumulated different proportions of material from different sources over time. The grooves cross the surface in patterns that create local geological complexity. The dust layer varies in thickness and cohesion across different terrain types. Choosing where to land and sample is itself a scientific decision, because the sample collected will carry the history of wherever it was taken from. Alongside the Phobos sample collection, MMX will also conduct extended observations of Deimos. The smaller moon has received significantly less attention from previous missions, partly because its greater distance from Mars makes close approaches more costly in terms of orbital fuel, and partly because the scientific questions about Phobos have historically been considered more urgent given its dramatic orbital fate. MMX's multi-year orbit in the Martian system will allow sustained observation of Deimos at resolutions and wavelength that no previous mission has achieved. There is something worth noticing in the design of this mission. It is international. JAXA leads the project, but French and German space agencies have contributed instruments. NASA has contributed scientific expertise and some hardware. The mission represents a collaboration across institutions that span different research traditions and different national histories of Mars exploration.
The sun return.
Whatever the sample ultimately tells us about the origin of the Martian moons will belong to a community rather than to a single program. That kind of shared investment in a question that has been open since 1877 has its own particular character. The people who named Phobos and Deimos, who photographed them for the first time, who lost 2 spacecraft trying to reach them in 1988, who mapped their surfaces across decades of intermittent orbital visits, none of them will be present when the sample returns to Earth. The chain of attention that connects Asaph Hall's discovery to the eventual laboratory analysis of Martian moon material is long enough that no individual life spans more than a portion of it. The scientists currently working on MMX analysis pipelines were not born when the Soviet Phobos missions failed. The engineers who built the Hayabusa sampler, whose design influenced MMX, were not alive when Mariner 9 took the first blurry photographs of the moons in 1971. The question persists across generations, not because any generation failed to answer it, but because the answer required tools and opportunities that took time to develop. This is how planetary science tends to work, at the scale where it is most honest about the difficulty of what it is attempting. The answer to where Phobos came from has always been available. In principle, it is encoded in the physical material of the moon itself, in the isotope ratios and mineral structures and compositional gradients that a returned sample would reveal. The answer has simply been locked away at a distance that took 1.5 centuries of technological development to bridge. The bridge is nearly built. When the sample returns, if the mission proceeds as planned, the analysis will take months or years. The results will enter the scientific literature with all the caution and qualification that rigorous analysis requires. They will be debated and extended and placed in the context of everything else that is known about the early solar system. The answer will not arrive as a single moment of revelation. It will arrive the way most answers arrive in science, gradually, through accumulating evidence, with the most important implications becoming clear only after the result has been examined from many angles by many people over a span of time. But it will arrive. The material will be here, on Earth, in a laboratory, accessible to instruments of a precision that no spacecraft has ever carried to Mars. That has not happened yet. It is, by most accounts, not far away. Step back far enough from Phobos and Deimos, and they become part of a larger question about the solar system itself. Mars sits at the inner edge of the asteroid belt. The belt is not a uniform ring of material. It is a population of millions of objects spread across a broad range of orbital distances, with composition varying in a recognizable pattern from the inner edge to the outer. The inner belt is dominated by rocky, silicate-rich bodies, relatively bright, relatively dense. The outer belt contains more of the dark, carbon-rich, water-bearing bodies, the C-type asteroids, among others. The boundary between these populations is not sharp, but the gradient is real and measurable. This gradient reflects the temperature structure of the early solar system. When the solar system was forming, the region close to the young sun was hot enough that only materials with high melting points could condense from the gas and dust of the protoplanetary disk. Silicates and metals survived. Volatile compounds, water ice, carbon compounds, organic molecules did not. They were pushed outward by the heat and pressure gradient of the young sun, condensing and accumulating in the colder outer regions of the disk. The frost line, the distance beyond which water ice could exist as a stable solid, sat somewhere in the vicinity of the outer asteroid belt during this early period. This is why the inner planets are rocky and relatively dry, and the outer solar system contains the great reservoirs of ice and volatile material. The chemistry followed the temperature, and the temperature followed the distance from the sun. Mars sits close enough to the inner edge of the asteroid belt that the distinction between the planet and the belt is partly a matter of orbital mechanics rather than physical character. The material that eventually built Mars came from a region of the disk that overlaps with the material that populated the inner and middle belt. The history of Mars and the history of the asteroid belt are connected, told from different perspectives on the same early solar system. Phobos and Deimos, sitting in orbit around Mars with compositions that resemble the outer belt, represent a puzzle in this context. If they are captured C-type asteroids, they arrived from the outer belt or from even farther out from the trans-Neptunian populations that some dynamical models suggest delivered carbon-rich material to the inner solar system during the period of heavy bombardment billions of years ago. Their presence in Martian orbit would then be a record of that delivery process, preserved in miniature in the orbits of two small dark bodies that had to be captured rather than impacting Mars or escaping back into the belt. If they formed from a giant impact, the C-type composition is harder to explain, but not impossible. The impactor could have been a carbon-rich outer belt body, and the material that was excavated from Mars and thrown into orbit could have mixed with impactor material in proportions that shifted the final composition toward what we observe. Or the composition match could be partly misleading. Space weathering could have altered the spectrum in ways that make Martian material look more asteroid-like than it actually is at depth. Either origin story places the Martian moons inside a larger narrative about how the early solar system moved material around. The first 100 million years of the solar system were violent in a way that is difficult to convey on human scales. The giant planets, Jupiter and Saturn in particular, migrated inward and outward from their formation positions as they interacted with the gas of the protoplanetary disk. Those migrations sent gravitational waves through the inner solar system, scattering material across orbital distances, triggering periods of intense bombardment on the inner planets, delivering outer solar system material to regions where it would not otherwise have arrived. The surfaces of the Moon, Mars, and Mercury still carry the scars of that era. Heavily cratered terrains, impact basins hundreds of kilometers across, geological records of a time when the inner solar system was being shaped by collisions at a rate that has not been matched since. Phobos and Deimos may be survivors of that era, or products of it, or both. They carry in their composition and their structure some record of what the early solar system was doing when they formed or were captured, and that record is part of why the sample return mission is considered scientifically important, beyond the specific question of Martian moon origins. Understanding how small bodies move through the solar system, how they are captured or created or disrupted, how composition varies across the disk, and how that composition is preserved or altered over billions of years. These questions extend well beyond Phobos and Deimos. But Phobos and Deimos are accessible. They are there, in orbit around a planet that has been visited by more spacecraft than any other planet in the solar system. They are small enough that reaching and sampling them is within the capability of current technology in a way that sampling a main belt asteroid in the outer belt is not. They are convenient targets for inconveniently large questions. There is a version of this story that stretches back to the earliest days of the solar system, to the disk of gas and dust around a young sun, to the gradients of temperature and composition, to the migrations of giant planets and the cascades of material they stirred up. Phobos and Deimos are the current chapter of that story, the part that is happening now, in the sense that the moons are still there, still orbiting, still carrying whatever they carried when they arrived or formed. Long before any telescope existed, the night sky above the Martian surface would have shown these two small objects moving through the dark. There was no one to see them then. The question of what they were made of and where they came from was not yet a question, it was simply a state of affairs. Unremarked and unexamined, the question became possible only when minds capable of asking it arrived on one of the neighboring planets and began to look outward. That happened recently, in cosmic terms, barely an eye blink. The questions that those minds have formulated about Phobos and Deimos are questions about origins, about the early solar system, about the processes that built the world those minds stand on, about how material moves through space over timescales that no civilization has yet existed long enough to directly observe. The two small moons carry the record. They are still carrying it, tonight, in orbit above a cold red planet, patient in the way that objects are patient, not waiting for anything, simply continuing. There is a thought experiment that planetary scientists sometimes use when they want to understand what is truly strange about the Martian moons. Imagine standing on the surface of Phobos, on the side that permanently faces Mars. Mars fills a significant portion of your sky, not the way the moon fills ours, which is a modest disk that you can cover with your thumbnail held at arm's length, but a presence large enough to dominate the visual field. The planet hangs there, its rust-colored surface and pale polar caps, visible in detail that no telescope on Earth can match, its thin atmosphere catching the light at the limb and producing a faint blue arc that separates the surface from the black of space. You would weigh almost nothing. A person of average mass standing on the Phobos surface would weigh roughly as much as a single sheet of paper weighs on Earth. The gravitational pull is so weak that the question of which direction is down becomes partly philosophical. The tidal force from Mars is comparable to the gravitational pull of the moon itself. And on the far side of Phobos, Mars actually pulls upward more strongly than Phobos pulls downward. Walking requires care. Running would likely result in leaving the surface entirely. The sky above you would be dark, and the stars would be sharp and steady in a way that no atmosphere softens. The sun would be there smaller than it appears from Earth, about 60% the apparent diameter, but still bright enough that looking directly at it would be damaging. Mars would be bright too, reflecting sunlight back toward you with a magnitude that would make it the most luminous object in the Phobos sky by a considerable margin. And then, once every 7 hours and 39 minutes, the surface beneath you would complete another orbit. You would not feel the motion. The orbit is smooth, the acceleration imperceptible at human scales. But the universe would move around you in a way that no human has ever experienced directly. Mars rotating slowly below your field of view, the stars sweeping overhead, the sun crossing the sky in under 4 hours, and then darkness again. No human has stood on Phobos. No human has stood anywhere but Earth and the moon. The thought experiment is only that a way of making the orbital mechanics and the surface conditions viscerally present, rather than abstractly numerical. But it points towards something that scientific description alone can sometimes miss. These are places, not data points, not orbital parameters, not spectral signatures. Places with surfaces and temperatures and skies, with particular ways that light falls across irregular terrain at different times of day, with the specific quality of silence that comes from a body too small and too airless to carry any sound at all. The human relationship with Phobos and Deimos has been almost entirely mediated by instruments and mathematics. No one has looked at the grooved surface of Phobos from below, looking up. No one has stood on Deimos and watched Mars turning slowly across the sky over the course of a day and a half. No one has experienced the particular darkness of either moon's far side, facing permanently away from the planet into the open interplanetary space beyond. These experiences remain entirely in the category of the imagined. They may not remain there indefinitely. Several mission concepts, at various stages of development over the past 2 decades, have proposed using Phobos or Deimos as a staging point for human exploration of Mars. The reasoning is practical. Landing on Mars itself requires descending through an atmosphere thin enough that standard parachute-based deceleration is marginal for heavy payloads, and returning to orbit requires launching against Martian gravity with a rocket large enough to matter. The Martian moons, by contrast, can be reached and departed with a fraction of the energy. A crew in orbit around Phobos could operate surface rovers on Mars with only a small communications delay, about 40 milliseconds for a signal round trip, compared to the many minute delays from Earth. The moons are not ideal in every sense, but they are accessible in ways that Mars itself is not. Whether humans will visit Phobos before or after they visit the surface of Mars, or instead of visiting the surface, or in conjunction with it, these are questions that depend on decisions not yet made, funding not yet allocated, technologies not yet developed to operational readiness. The timelines for human outer solar system exploration have shifted many times in the decades since the Apollo program demonstrated that humans could reach another world. What has not shifted is the direction of attention. Mars and its vicinity remain the most discussed destination for human spaceflight beyond the Moon. Phobos sits in orbit above the most discussed destination. There is something gently persistent about that position. The Moon has been there long before the discussion began, long before the species doing the discussing existed, long before Earth had anything in its biosphere capable of looking upward and wondering about the reddish point in the sky. The grooves on its surface were forming slowly, over millions of years, when the first fish were leaving the oceans of Earth to test the edges of land. Stickney Crater was already ancient when the first forests were growing. The inward drift of the orbit was already measurable in principle, if not yet in practice, when the first cities were being built on river plains in the ancient world. Every grandmother who ever pointed at the red wandering star on a clear night and passed its name to a child, who asked every one of those moments happened while Phobos was already doing what it is doing now, orbiting, drifting inward, carrying its unresolved questions in a silence that the solar system does not break. The questions have been there a long time. The people working on them now are the first generation with instruments capable of beginning to answer them. That is not a small thing, even if it does not feel dramatic. The sample return mission, the orbital measurements, the decades of accumulated imaging, the dynamical models of the early solar system, all of it is the current chapter of an inquiry that began the first time a human mind turned its attention to the red wandering star and began to wonder what surrounded it. That wondering has not stopped. It has only become more precise. And in the becoming more precise, the moons have come into focus in a way that the night sky alone could never have provided. 2 irregular, dark, slow-turning bodies above a red planet, one falling, one drifting, both carrying inside them a record of the early solar system that no instrument has yet fully read. The surface of Phobos is cold tonight. The grooves are there, as they have always been, fractured in their quiet way by a force that works without urgency and without pause. Mars turns below. The orbit keeps its slow tightening, indifferent to whether anyone is watching. The night sky above the southern hemisphere tonight contains a reddish point that has been watched for longer than any written record exists. It moves against the background stars over weeks and months, tracing its slow path through the constellations in the way that all planets do, not fixed, not flickering, but steady and wandering in a motion that the ancients found meaningful and that astronomers now describe in equations that can place it within a fraction of an arcsecond at any moment across millions of years of past or future time. Above it, invisible from any ground-based telescope and invisible to the naked eye, 2 small dark bodies continue their orbits. They have been orbiting since before any human looked up. They were orbiting when the first civilizations were counting seasons by the position of planets in the sky, assigning names to the wandering red light, building calendars and myths around its movements. They were orbiting when the first telescopes were turned toward Mars, and astronomers began the slow accumulation of knowledge about what the planet's surface and atmosphere contained. They were orbiting when Asaph Hall found them in August of 1877, when the Soviet missions failed in 1988 and 1989, when Mars Express made its careful, close approach in 2010. They are orbiting now. There is a particular quality to the persistence of physical objects that no story can quite capture. A moon does not continue its orbit because it is dedicated to continuing. It continues because the mathematics of its situation offers no other option at this moment in its history. The orbit is the path of least resistance through a gravitational field that has been shaping it for longer than life has existed on Earth. And yet the persistence feels like something. The constancy of it, the indifference of it, the way that Phobos keeps circling Mars, regardless of whether any instrument is pointed at it or any mind is considering its fate. There is something in that which is easier to feel than to explain. The question of what Phobos is made of inside has been there since the day it was discovered. It was there before it was discovered encoded in the material of the moon, waiting for a question precise enough to find it. The isotope ratios in the rock beneath the surface regolith have held the answer to the origin debate for billions of years. They held it while the question was not yet being asked, while the instruments capable of asking it did not exist, while the civilization capable of building those instruments was still learning how to write. They are still holding it. There is a version of the next decade in which a spacecraft returns to Earth with material from beneath the surface of Phobos, and the analysis of that material finally places the origin question on the side of one hypothesis or the other, with the kind of evidence that settles debates. In that version, the answer that has been waiting in the rock for billions of years becomes the answer that the scientific community can examine, replicate, and build upon. That version may arrive. It may arrive in the way that most scientific resolutions arrive not as a sudden clarity, but as a gradual accumulation of detail, each piece of evidence shifting the weight slightly. The final picture, emerging only after many people have looked at the same data from many different angles over a span of years. Whatever the sample reveals, the moons will still be there. Phobos will still be drifting inward at 1.8 centimeters per year, its surface grooves still widening imperceptibly under tidal stress, its interior still holding whatever structure it has always held. Deimos will still be drifting outward, patient and dim, crossing the Shamash sky over 2.5 days, with a steadiness that navigators might have trusted if they had ever stood on the Martian surface and needed a fixed reference in the dark. The solar system does not reorganize itself around the conclusions of a returned sample. What changes is only the knowledge, and knowledge, once added, does not leave. It becomes part of the foundation for the next question, which will be asked by people who take the current answer for granted, in the way that the current generation takes Hall's discovery for granted, the way that future generations will take whatever the sample returns as simply part of the known. The chain of attention extends forward. It has always extended forward, from each generation's instruments and questions to the instruments and question that those findings made possible. It extended from Asaph Hall's telescope in 1877 to the first blurry photographs of 1971, to the detailed surface maps of the Viking era, to the density measurements of Mars Express, to the sample return mission that is currently being prepared. At each step, the moons were already there. The dark surface of Phobos, the smoother terrain of Deimos, the grooves that record a slow fracturing, the inward drift that records a slow ending, all of this was in place before any of it was known. The universe does not wait for observers to arrange its conditions. It simply presents conditions, and observers arrive or do not, and when they arrive, they find things that have been the case for a very long time. Tonight, two small worlds orbit above a red planet that most people on Earth have looked at without knowing what it was. The light from Mars is arriving right now at whatever surface is beneath an open sky, completing a journey of several light minutes from a planet with two dark irregular moons in quiet orbit around it. The light does not carry any information about the moons. They are too small and too dark to contribute anything detectable to what leaves the Martian system and crosses the distance to Earth. But they are there in the light in the sense that they exist in the same system that produces it, part of the same small corner of the solar system that the red wandering star has always indicated. Somewhere above Mars, the orbit turns. 1.8 centimeters closer than last year, the surface holds its cold. The dark between the stars remains. The light keeps arriving.